Hey guys, in this video we are going to look at the case 1 of a Routh stability criterion, the first example. So Routh stability problems are very easy to solve. There are basically three cases in this. There are three cases where in the first case this is called a normal array. So there are no zero elements in the first column. In the second column, in the second case, we have a row of zeros, and in the third case, we have the first element of a column as zero. And we're going to look at all the three cases closely with example, and you will have a better picture of what each case is once you go through that. Okay. So in exams, you will be given a characteristic equation. So all you will be given is this is the characteristic equation of this system. Find out if the system is stable, unstable, or marginally stable. So the first thing that you have to do is build something called the Routh array. So the Routh array is very easy. You have to build the first two rows by going with the powers of the equation. So if you look at this characteristic equation, which is s power 4 plus 8s cubed plus 18s squared plus 16s plus 5, the highest power in this equation is 4 and the second highest is 3. So what you have to do is, the first step, write down the coefficients of all the even powers followed by the coefficients of all the odd powers. So the first one is s power 4 and the second one is s power 3. So I'm going to write down all the even powers coefficients in the first row. So that would be coefficient of s power 4 is 1, coefficient of s square, the next even power is s square, right, 18, and the next even power is s power 0, right, so that would be 5. And in the second row, I'm going to write down the coefficients of all the odd powers. And here I have two odd powers, which are s cube and s power 1. So that would be 8 and 16. So from now on, we have to build something called the Routh array. The building of the Routh array is a very simple, just a simple mathematical operation. And whenever you construct this array, just keep in mind that the first column of the array is very important, and this is what forms the base for all your calculations. Okay. So what will be the next row that I'm going to build? I'm going to build s power 2. Okay. So to have s power 2, the first thing that I need is the previous row. So what is the previous row? S cube row. What is the first column element? 8. So my base, the denominator, is going to be 8. Okay. And in the numerator, it is going to be 8 into 18, the product of these two minus product of these two. Okay. So that would be 8 into 18 minus 16 into 1. This is how you will keep obtaining the elements of each column. But if you look at this one, you might have just thought, hey, this 8 and 16, you could have simplified this further, right? Which is why whenever you have a row with a GCF, with a GCD or HCF higher than 1, right? In those cases, divide the entire row with that GCD. That way, your mathematical calculations are going to be so much more easier, which makes our life easier, right? So I'm going to divide this whole row by 8. 8 by 8 is 1 and 16 by 8 is 2. So, what would this be? My base is now going to be 1, and 1 into 18 is 18 minus 2 into 1 is 2. So this is 16 by 1. So 16 is my first element. So 16 is the first element of my row s square. What about this element? What about this element? the base is always the previous row's first column element, which is 1, and again the product of these two minus product of these two. So whenever you're finding out for column 1, you take the column 2 and multiply with column 1. You need to find for column 2, you take column 1 previous row and column 3 the next one, right? So for to obtain this one, I would have to take the product of 1 and 5 minus 1 and 0. So that would be 5 minus 0, which is 5. Make sense? However, if I say for example I had another element here which I had to get, for that I would take the product of 1 and whatever is here minus 1 into this one. But I don't have any, not today's headache. So this is how I got the row of S square. The next step is the row of S power 1. What is the previous row's first column element? 16, right? 16 is the previous row's first. Do I have a GCF, GCD or HCF? I'm sorry, I don't. So I can't divide it, I can't simplify it further. So 16 is the base. So 16 into what is this element? 16 into 2 minus 5 into 1, which is 32 minus 5 by 16. 32 minus 5 is 27. 27 by 16 would be 1.6, 1.6, right? So now to obtain this element, I would need to multiply. I'll get rid of these lines for you. So to obtain this element, my base would still be 16, right? The previous row's first column. So 16 into what is the next column? 16 into 0 minus 1 into 0, right? So this would be 0. So I don't even have to write that element, okay? So in your exam, whenever you're solving questions like this, just make sure that you also show the calculations on one side of the page, or make the calculation, update the table, keep doing that so that there is a picture, it is understood that you are solving it, okay? The last one that we need to obtain is S power 0. How do I obtain this one? So this one is 0, right? So my base is 1.6, previous row. So 1.6 into 5 minus 16 into 0, right? 1.6 into 5 minus 16 into 0. So 16 into 0 is 0. 1.6 into 5 is, I don't have to get that, right? 1.6 and 1.6 gets cancelled, and what I have left is 5. So now my Routh array is complete. My Routh array is now complete, which means I can determine if the system that has this characteristic equation is stable, unstable, or marginally stable. And the other thing that I can do is also decide how many roots lie where. So remember, I told you the Routh array is entirely based on the first column. Okay. So from the first element to the last, do you see anywhere a change of sign? All these are positive, right? So from top to bottom, there is absolutely no change of sign. Every element is positive, which means there are no roots lying on the positive half of the S-plane, okay, which means that the system is stable. So if there are roots on the positive half, the system is unstable. If the roots are on the imaginary axis, the system is marginally stable. If the roots are on the negative half of the S-plane, the system is stable. Since there are no sign changes here, the system is considered to be stable. However, if you are given some different characteristic equation and then you have found out that you have gotten a minus 16 here. I'm just throwing it in there so that if you have this situation, you will come up with an answer like this. So for the previous example, what was the answer? You are going to write a conclusion saying the system is stable and all the roots are lying on the negative half of the S-plane. Why are they lying on the negative half of the S-plane? Because the system is stable, right? There are no sign changes means the system is stable, which is why the roots are all on the negative half of the S-plane. However, if there is a situation where one of the signs is negative, you need to count how many times the sign has changed. Here it is positive, correct? And then when you came here, it has become negative. Sign change number 1. Here it is negative and here it became positive. Sign change number 2. So on the whole, from top to bottom, the sign has changed twice, which means there are 2 roots, 1 and 2 roots lying on the positive half of the S-plane, which means the system is unstable. And in conclusion, you will also write there are 2 roots lying on the positive half of the S-plane. What if there are zeros? That is a different case altogether, which does not fall in case 1 of the Routh stability criterion. So this is a classic example of case 1, which is a normal Routh array. Hope you have found this informative, and if you have an exam coming up, I wish you the best.